Hi everyone, my name is Samuil, and today I'll be talking you through our paper on latent generative replay, which is a method for performing resource-efficient continual learning of facial expressions. I'll start with the motivation behind the paper. And first, what is continual learning? In continual learning, we are interested in cases where data is made available continuously as a stream, and we want to learn knowledge incrementally. To illustrate this with a specific example, on the right you can see an example of a continual learning scenario known as task incremental learning. Here you have 8 emotions that you want to classify, but instead of learning them all at the same time, you split those into 4 tasks that you want to learn to solve incrementally. So you first feed the model examples of only sadness and contempt, then you only train it on happy and neutral, and so on. And by the end of the 4th task, ideally you want your model to do well on all 4 tasks. However, if you were to simply train the model sequentially, first on the first task, then on the second, and so on, you would overwrite previous knowledge, and your model's performance would gradually deteriorate on previous tasks, and that's a phenomenon known as catastrophic forgetting. To address catastrophic forgetting, various continual learning approaches have been proposed, and one family of continual learning approaches are rehearsal methods. The most straightforward example is naive replay, which you see on the left. Here you maintain a replay buffer containing previously seen samples, and when you encounter a new task, you train the model on a combination of new data from the new task and randomly sampled old data coming from the replay buffer. Since you're physically storing training samples though, this method can be inefficient, especially if you're training on high-dimensional data. And a more efficient rehearsal approach is latent replay, which you see on the right. Here the idea is that instead of replaying the actual input samples, you store and replay only latent representations from the middle, while you pre-train the lower layers of the network, also known as the root, and keep them frozen. Since those latent representations you replay are smaller, the replay buffer is also smaller, and the method is more efficient. Another continual learning approach is known as deep generative replay, or DGR. And here the idea is that as you learn new tasks, you also maintain a generative model, which can generate synthetic samples resembling previously seen data. Again, we interleave new data with old data. However, this time the old data doesn't come from a replay buffer, but instead it's synthetically generated by a generative model. There is also a slight variation of this algorithm, known as DGR with distillation. And without going into too much detail, the main idea behind distillation is that instead of training the model on hard targets or labels, you use soft targets using the softmax function. And that's been known to often improve predictive performance. Continual learning approaches tend to incur extra computational costs, since you either maintain a replay buffer or maintain a generative model. And most of the continual learning approaches out there optimize solely for accuracy, ignoring the resource consumption of the algorithm. However, we often want to deploy continual learning on resource-constrained devices such as robots or mobile phones, which makes resource efficiency an important aspect of performance. And now I'll talk you through our proposed method, latent generative replay. The basic idea behind latent generative replay, or LGR, is that we use the insights from latent replay to modify the existing deep generative replay algorithm and make it more resource efficient. To do that, we introduced a few modifications. First of all, instead of generating input samples, we generate latent representations and replay them from the latent replay layer in the middle. Since those latent representations are smaller than the input samples, we now have a smaller generative model, which consumes less memory and is faster to train. And finally, just like the authors of the latent replay algorithm did, we pre-train and freeze the first several layers of the neural network, so that only the last layers, which you call the top of the network, are modified during training. And just like with DGR with distillation, you can also use the distillation approach here as well. We call that similarly LGR with distillation. Now I'll go through how we evaluated our proposed method. Like I said, we wanted to evaluate our method in the context of facial expression recognition. To do that, we used 3 popular facial expression benchmarks. The first one is the CK+ dataset. That's a relatively small dataset, and images are standardized. So they've been obtained in a lab setting with people facing the camera. Next one is RAVDB. It's still not too big, but unlike CK+, it consists of images taken in the wild. So people in more natural settings, not always facing the camera. And the last one is AffectNet, which is a very big dataset, and it's also the most complex of the 3. To evaluate our proposed methods, LGR and LGR with distillation, we benchmark them against the methods I mentioned earlier. So those are naive replay, latent replay, and also DGR and DGR with distillation. For the main set of experiments, which we report in the next slides, we use a pre-trained VGG16 feature extractor as the root of the network. And we also performed an ablation study using AlexNet, MobileNet, and ResNet, where we observed similar trends, but we found that VGG16 had the best overall performance. We evaluate all of the compared approaches on task incremental learning, where we randomly split the facial expression classes into groups of 2 and train the model one task at a time. During training, we keep track of average accuracy across all tasks as a measure of predictive performance. And to gauge resource efficiency, we also log the training time in seconds, RAM and GPU memory as a measure of memory cost, as well as CPU and GPU usage as a measure of processing cost. And with that experiment setup in mind, I'll highlight some of the results from the evaluation. In this table, you can see each of the 6 compared approaches and their corresponding metrics on the CK+ dataset. The green arrows provide a direct comparison between DGR and LGR. And you can see that our method LGR outperforms the DGR methods across nearly all metrics. And more importantly, it also outperforms rehearsal methods in some areas, for example, reporting the lowest GPU memory consumption across all methods while keeping accuracy competitive. We observe a similar situation in the RAFDB experiments. LGR beats DGR on almost all metrics. It also reports the best accuracy among all compared approaches, and it still deals very well in memory consumption, narrowly behind Latent replay. And finally, the AffectNet results. Here again, LGR reports the lowest GPU memory consumption of all methods, but it also has the highest accuracy, the second highest accuracy. So in this case, it has outperformed rehearsal methods in terms of both accuracy and resource efficiency. So to conclude the presentation, we gave you a brief overview of the LGR method as an alternative method for performing continual learning on facial expressions. We show that it outperforms DGR across nearly all compared metrics. And even when you compare it to rehearsal methods, it can still offer memory savings without impacting accuracy, sometimes even improving accuracy. So overall, we believe LGR provides a good balance between predictive performance and resource efficiency. As for next steps, some things we're interested in studying next are, for example, exploring slowing down of the route instead of freezing it completely. Also, we'd like to analyze further the quality of the representations our generative model is producing. And lastly, we'd be interested to extend the approach to other continual learning approaches, such as iCarol and GEM. Lastly, I would like to thank my co-authors as well as our sponsors. Thank you all for listening.